Today, we're diving into something that's sometimes called the mathematics of mathematics. That's a pretty grand title, I know. It's called category theory. Our goal here is pretty simple: to build a real intuition for what that actually means and why it's such an incredibly powerful way to think about, well, pretty much everything.
All right, let's start with a little puzzle. Think about it for a second. What on earth could people in a family tree, all the numbers on a number line, and every single account on a social network possibly have in common? They seem completely different, right?
Well, the answer is actually, it's kind of beautiful in its simplicity. It's all about relationships. The key is to stop focusing on the things themselves, the people, the numbers, the accounts, and instead focus on how they're all connected. That one idea, that shift in perspective, that's the heart of category theory.
Okay, so this idea of focusing on relationships, how does that get us to a mathematics of mathematics? What does that even mean? Let's unpack that.
This quote about Galileo is the perfect way to think about it. Imagine trying to describe the complex, three-dimensional flight of a bird. It's tough. But what did Galileo do? He didn't just stare at the bird. He looked at its shadow on the ground. That's a 2D projection. And he tracked its height. That's a 1D projection. By understanding these two much simpler relationships, he could piece together the entire complicated flight. Category theory does the exact same thing, but for all of mathematics. It simplifies things by focusing on the shadows, the relationships. So, to really get our hands on this big idea, we need to know what the building blocks are. And you know what? In category theory, it really all boils down to one thing: arrows. So what is a category? Formally, it's just a collection of three things. First, you've got objects. Just think of them as dots. Second, you have arrows that go between the objects. And third, there's a rule called composition. All it says is that if you can get from A to B with an arrow and from B to C with another arrow, then there has to be a shortcut arrow that takes you directly from A to C. That's it. That's the entire foundation: objects, arrows, and a way to compose them. Now, the most classic go-to example is something called the category of sets, or just set. Here, the objects are, well, they're sets. No surprises there. And the arrows between them? They're just the functions you learned about in school, the things that map elements from one set to another. Composition is just what you'd expect: function composition. Pretty straightforward, right? But hold on, because here is where things get really interesting, really powerful. As Tom Leinster says, the objects don't have to be anything like sets. This is the big mental leap. It means we can totally forget about what's inside the objects. We can just treat them as abstract dots and focus entirely on the arrows, the relationships between them. Just how far can we take this idea? Well, think about something as simple as numbers, with the less than or equal to relation. Turns out that's a category. The objects are just the numbers, 1, 2, 3, and so on. And an arrow? We just say an arrow goes from A to B if, and only if, A is less than or equal to B. So what's the composition rule? It's just transitivity. We all know if A is less than or equal to B, and B is less than or equal to C, then A has to be less than or equal to C. All of a sudden, this simple ordering rule is a full-blown category.
Okay, get ready for a trick that is so simple it almost feels like cheating, but its consequences are absolutely profound. Let's talk about the power of reversal.
Here's the move. You take any category you want. You keep all the objects exactly where they are, and then for every single arrow, you just flip it around. That's it. You just reverse its direction. Any arrow that pointed from A to B now points from B to A. This new thing is called the opposite category. Now, why does that matter? Because that one simple flip gives us something incredible called the principle of duality. What it means is that for every single statement or theorem you prove in category theory, you get a second one completely for free. You just take your statement, reverse all the arrows, and bam, you have a brand new, equally true statement. It literally doubles your mathematical knowledge with almost zero extra work. Let's see how this works. We can define something called an initial object. It's basically a universal starting point. It's an object that has exactly one arrow pointing out of it to every other object in the category. In our category of sets, the perfect example is the empty set. There's only one possible function you can define from the empty set to any other set. Now, watch this. Let's use our duality trick. What happens if we just reverse the arrows in the definition of an initial object? Well, we get its dual, a terminal object. Instead of having one arrow going out to everything, it has one arrow coming in from everything else. It's a universal endpoint, a sink. And in the category of sets, what is it? Any set with just one single element in it. So we figured out how to think about what's going on inside a single category. But the real magic, the true power of this whole approach, comes from building bridges that connect completely different mathematical worlds. And the way we do that is with something called a functor. Here's the analogy. If a category is its own little mathematical universe, then a functor is like a spaceship that lets you travel between them. It's a map between categories. It takes the objects from one universe to the objects in another, and it does the same for the arrows, all while making sure the basic rules of composition stand intact. It's a translator that preserves the structure. A really common and useful example is a forgetful functor. So imagine we have the category of groups. Its objects are sets, but they also have some extra structure, like rules for multiplication. A forgetful functor can map this world to the much simpler category of sets by just forgetting about the extra rules. It takes a group and just hands you back the raw set of elements underneath. It's a way of looking at a problem by intentionally throwing away some information to see the simpler picture. So what's the big deal? Well, functors are these amazing translators. They let you take a really gnarly, difficult problem in one area of math, translate it into a different, simpler universe where you can actually solve it, and then you can translate the solution back. It's this unbelievable tool for moving ideas and solutions between worlds that you never even thought were connected. Okay, I know that was a lot, and believe me, we have only just scratched the surface here. But if any of this has piqued your interest, if you're thinking, wow, that's a cool way to see things, then your journey can absolutely start right here. So the obvious next question is, okay, I'm sold. Where do I actually start? How do I really learn this stuff without getting completely lost? Well, we've got you covered. Based on the sources we looked at, here are 3 fantastic paths, depending on where you're coming from. If you're an absolute beginner and just want the intuition without the scary formalism, you have to check out Conceptual Mathematics by Lavery and Chanuel. It needs 0 prerequisites. Now, if you've got some college-level math, Tom Leinster's Basic Category Theory is a wonderfully clear and concise formal introduction. And finally, if you're already a practicing mathematician and want to see how all this connects to everything else, then Emily Reel's Category Theory and Context is definitely the book for you. And I just want to leave you with this one final thought from Peter Johnstone because it really gets to the soul of category theory. He says that by forgetting the explicit structure, you will be forced to concentrate on the essential aspects of this problem. You see, it's not just about getting the right answer. It's about stripping away all the noise to understand the problem's true shape. It's about learning how to ask much, much better questions. And that is the real power of category theory.